In our previous work, we've studied systems of two linear equations in two variables. We can add more equations and more variables to a system, and we'll do it in a kind of systematic way in order to get a unique solution. If a system has more equations than it has variables, that system is called overdetermined. It will typically have no solutions. And the reason it will have no solutions is that it has too much information. To see what I mean by that, consider this system. Here we have three equations and two variables. We're looking at three lines in a plane. So y equals x minus 2, that's this line. Y equals negative a half x plus 1, that's this line. And y equals 2x minus 1, that's this line. And we see that every pair of lines has an intersection. Every pair of equations has a shared solution. But there's no point where all three lines intersect. There's no solution shared by all three equations. And that's always going to happen if we write down three random lines, right? If we just draw three random lines, they're not going to all meet at a point. Occasionally we'll get very lucky, and they will all have a point in common, but typically, three lines just won't meet. So, an overdetermined system will typically have no solution. We can also have an underdetermined system. An underdetermined system has fewer equations than it has variables, and it will typically have infinitely many solutions. The reason for that is that an underdetermined system has too little information to narrow down to a single point. This is kind of boring to see in two variables, because the only way to have fewer equations than variables is to have only one equation. So here's the graph of 5x plus 2y equals 8. And you can see it's just a single line. Every point on the line is a solution to this quote-unquote system. It feels strange to call that a system because it only has one equation. As we add more variables, we can add more equations. So the same thing will apply to a system with 3 variables and 2 equations, or 6 variables and 5 equations, or 119 variables and 115 equations. If we have more variables than we have equations, we have an undetermined system with infinitely many solutions. Okay, so when we want to actually solve a system, what we want to have is what's called a balanced system. In a balanced system, the number of equations is equal to the number of variables. For the rest of this section, we're only going to concern ourselves with systems of 3 linear equations in 3 variables. But the techniques that we use for 3 equations in 3 variables can also be used for 4 equations in 4 variables, or 5 equations in 5 variables, at least in principle. In practice, it becomes very, very tedious to solve large systems this way, and so we have more advanced techniques available to solve larger systems, including having a computer do it. Solving large systems is actually one of the main purposes for which the computer was invented, and it's something that computers do very well. So we study systems of 3 equations and 3 variables fully by hand. For larger systems, we want to learn more advanced algebra techniques, which we'll do in a later course. And ultimately, we want to learn computational techniques to allow a computer to do it efficiently. Now, there's a typically In all of those descriptions, overdetermined systems will typically have no solution. Sometimes we get very lucky and all three lines meet at a point. Underdetermined systems will typically have infinitely many solutions. Sometimes we get very unlucky and they end up having no solution. Balanced systems will typically have exactly one solution. A variety of things can go wrong there, which we'll see later in this section.